Okay, so I believe it's where we left off. We've been talking about titrations and titration curves. We talked about two types so far, really, in sort of depth. We talked about the titration of a strong acid with a strong base. We also talked about a titration of a weak acid with a strong base. Both of those curves look a little bit different than the one we're looking at here, which is where I think we left off, which is talking about a strong acid and a weak base titration. Remember that when we look at these titration curves, there's really four parts to the titration curve. There's really before you start the titration, so before you add any of the titrant to it. There's also once you start the titration before the equivalence point, and there is at the equivalence point. There is then after the equivalence point, which would be our fourth spot along the way. So this is one that we were looking at, like an example of HCl plus some ammonia. Ammonia being our weak base, HCl being our strong acid. Going to make ammonium chloride here, which you could either keep together or break apart. Your choice, really, in this particular case. And again, in this titration, as we started to talk about last time, is a little bit different. In this case, we are adding the base here to our acid. So our acid's actually on the bottom there. So we're adding the base to our acid in this case. And that's why we see the curve, as we talked about, kind of upside down. And that's because at the very beginning, I'm sorry, I put that backwards, didn't I? Let's try that again. That is not how we're doing that. Take two, try that again. Here we go. Otherwise, my curve would look the other way, I suppose. The NH3 is in the bottom here, and we're actually adding the acid in this case. There we go. That looks a little better. All right, so we're actually adding the acid to our base, and again, that's why our pH here is actually starting high, because what we have to start with is just a base in the flask or the beaker or whatever we're titrating with. And I think we got to that part of the titration, which is before we actually start adding any HCl in this case. And before we add any HCl, we really just have the weak base. So as we talked about, to solve for the pH of it, you would do really a KB type of problem, where this is going to accept the H plus, make NH4 plus, and hydroxide in this case. This would be an ice table. And you can use molarity at this point because we have not added any of the HCl to it. We would obviously use a KB for NH3 in this case. And again, here we would solve for X, either making an assumption using the quadratic. When we do solve for X, that will equal the hydroxide concentration as we talked about. And that means that we will be able to get to the POH and then to the pH. So as we talked about, this one is very similar at the beginning as to the last one that we talked about, which was the weak acid and the strong base, except that you have a weak base versus a weak acid in this particular one. And again, at the very beginning here, you haven't added anything, so you could just go with the molarity. Now, when we look at what happens when we start adding, again, all the way to the equivalence point here, we do see that the pH is starting to drop, which does make sense since we are adding acid to it, right? So we should expect the pH to start going down. And at that point, we are obviously going to get a reaction between our HCl and our ammonia in this case. And we're going to get, again, our ammonium chloride, really. And again, if we are at that second point, which is before the equivalence point, as we've been doing with all the other examples, we know a couple of things. We should be doing this in moles. So I'm going to make up my moles of acid, which is what I'm starting with. Again, here I'm, sorry, to the moles of the base. I'm so backwards on this one today. All right, I'm going to do the moles of the base here. And since I am adding the HCl, I'll get that right before we're done today. Try that again. There we go. I know. This is my first day. See, I'm not really a teacher. It's my costume. That's right. All right. So that is the base is what we are starting with there in the beaker. And we are adding this guy here. So if we start with our 4 moles of ammonia in this case, obviously, as we've talked about, we do know that at the equivalence point, the moles of the acid and the base should equal each other. So in this particular case, since we are adding the HCl, we should have less moles than what we started with. So again, here I'll just make up 2 moles, and we would have 0 of these guys either together or separate, depending on how you want to write it. At this point, it is the HCl that we're adding as the limiting reagent. So we will have -2, and +2 moles on the opposite side here. That gives us 0 of this. We'll end up with 2 moles of our NH3. We'll have 2 moles of this guy and 2 moles of this guy. At this point, we can convert everybody back into molarity, and obviously we would use our total volume at that point, how much of the ammonia we started with and how much of the HCl we added to it. Obviously, if you kept ammonium chloride together on the right-hand side, you would just have one number at that point, which you could do as well. At this point, we want to kind of see what we got going on. So since I did separate it, we got 3 things sort of happening. We have chloride, which is a neutral salt, right? Because it comes from HCl, which means really we don't have to worry about that guy. We do have NH4 plus and NH3 left over. NH4 plus and NH3 is a buffer. Those are 2 things that are related to each other. That is a weak base and its conjugate acid, which means that we have just made a buffer in this particular case. And because we've made a buffer at this point, we can go obviously into an ice table if you wanted to. You could actually do 2 different ice tables. I could either do a KB ice table, which then you have to convert to pH with the NH3. You could do a Ka ice table with the NH4 plus and the appropriate Ka value. The much easier approach is to use our Henderson-Hasselbalch equation here. pH equals pKa plus the log of the base over the acid. And obviously, in this case, you do want to make sure of a couple of things. You want to make sure that you are using the pKa and not the pKb. You most likely in this problem would be given the Kb value there for NH3. So again, you could either convert it to a Ka and then to a pKa. You could convert it to a pKb, subtract 14 to the pKa like we've been talking about. So there's multiple ways you could get it, but you do want to make sure that you're actually using, again, the pKa value, not like the pKb value by accident here. Obviously, we want to make sure we get our base over our acid. This is going to yield you a buffer, obviously. It's going to yield you a basic buffer, which is what we can see in the picture. We are still basic pretty much through most of that. Towards the equivalence point, obviously we become acidic near it. But just like the previous titration in that sort of second region, you will always hit a buffer that's formed. It will always be a basic buffer. So just like the last one there with the weak acid and strong base, at this point in the titration, you have to do at least 1 ice table. The purpose of the ice table is to figure out really the buffer that you made, so the concentration of the buffer that you made, and then you can either again go into a table or into the Henderson-Hasselbalch equation. Any questions on that point in titration? So far very similar to the last one, except that instead of going from sort of acidic to basic, we're starting at basic and kind of working our way back down. That brings us to the third part of this titration, which is at the equivalence point. And let's talk about what happens there, which is at the equivalence point. And when we're at the equivalence point, we do know again that our moles of our base will equal the moles of our acids. So once again, we will have our reaction here. And we're going to, again, I'm going to get this right here. We're going to start with that. We're going to add our HCl. So if we start with our made up 4 moles here of our NH3, we know again that we should have exactly 4 moles of the acid that we're adding. We also, I think, talked about this last time, that in several problems, or a lot of problems, They may not give you the volume to reach the equivalence point. Again, there's multiple ways you could kind of figure it out. So I think we went over it last time, but just to remind you, we know that the moles of each of those things should be the same. So you kind of know how many moles you need to add, and you usually will know the molarity of whatever you're adding. So you can use those two things to figure out the volume that you need to get there. If it's a one-to-one relationship, you can use M1 V1 equals M2 V2 to figure it out. And really quickly, again, if they are really the same concentration and it's a one-to-one relationship, you need pretty much the same volume to reach the equivalence point as you do it. So there's a few ways that sometimes you do need to figure out the volume at the equivalence point, because we do need to turn it back to molarity right after the first table. So we want to figure out how much we need to add to do that. At this point, we would have 0 of each of these guys. And obviously here we can't choose a wrong number, I think. So it's got to be the 4 across the board. And that's going to give us what we expect to happen at the equivalence point, which is our acid and base is pretty much going to get used up. We will have then 4 moles of this guy and 4 moles of this guy. Once again, we'll use our total volume to convert back to molarity. And at this point, what we're really left with is I have been breaking this guy up, but we're really left with a salt, right? Which is, in this case, ammonium chloride. And that salt is pretty much how I broke it up there. We have an ammonium and chloride. As we talked about a second ago, obviously here the chloride comes from HCl, which means it's going to be neutral and not affect the pH. But the NH4, will it do anything? It will, because again, it comes from this weak base, right? So it comes from this weak base, which means it's going to be relatively strong. So just like we saw in the last titration, we will again have a hydrolysis reaction that's going to happen with that part of the salt. The NH4 plus, once again, if you're not sure what it's going to do, because it comes from a weak base, it should then act as an acid, basically. And it will act as an acid when it is reacting with water, which means it's going to send the H plus over to water. And in that case, we will make NH3 and a little H3O plus. So once again, here we should know that the equivalence point should be acidic, basic, or neutral. Should be acidic in this case, as we are generating some H plus. And we will take our molarity from above and basically transfer it down to here, right? This will then be a table with X's. This is going to go into our K, A, B, C, D, E, F, G, or K, A, right? Again, we want to make sure that we use a Ka value as we have generated H3O plus. Once again, you're going to probably have the Kb value given to you or looked up. So you want to use that Kw to switch it out to a Ka. Here we'll go through and solve for X. And at this point, as we can see from the table, our X equals the H plus concentration, which means we could then go directly into the pH and get it. So just like the last titration, when you reach the equivalence point here, because you started with really a weak base there, you will generate a salt that will go through hydrolysis, and it will always be an acidic salt. So always basically donate the H plus and produce H3O plus, and you could get the pH from it. Any questions on that there? By the way, the step previously where we did make the buffer is another example, like we talked about last time, that you can do a reaction, in this case, of a strong acid with a weak base, and we actually generated a buffer, right? Just like we kind of did on the other one as well. Any questions on the third spot there? All right, then the fourth spot is after the equivalence point. So we're going to continue to titrate here after the equivalence point. And again, obviously, we will have our reaction. And like normal here, we want to do it in moles. We're adding, and we are starting. So again, if we started with our 4 moles of NH3, because we are past the equivalence point at this point, we actually should, again, in this case, have more moles of the HCl. So again, I'll just make up a number of 6, which puts us well past the equivalence point. Again, as we talked about, you can compare your moles that you're starting with on the left-hand side there. And if whatever you're adding is less moles than what you started with, then you're before the equivalence point, right? And if you have equal moles, as we just saw, you're at the equivalence point. And if whatever you're adding is more moles than what you started with, you are past the equivalence point. So again, the ice table can really help you determine sort of where you're at. And as we talked about before, that's sometimes helpful because you should know kind of the type of calculation you should be doing at that point based on where you are in the titration curve. So in this case, what happens is our kind of switch. So our base in this case will become the limiting reagent. We got plenty of this guy. So the change has always got to be the smaller number for logical reasons of you cannot have a negative concentration. So always pick the smaller number. Even when your heart tells you not to pick the smaller number, pick the smaller number. Yes. 0, 4 moles. I look forward to watching that conversation as you're taking your exam. I don't know, should I take it? No, maybe I should. All right, we're going to convert everybody back into molarity. So once again, here we got a couple of things working. I again separated it, but we basically have our ammonium chloride salt happening, which is a salt. And clearly, as we just talked about, is going to go through hydrolysis. At least part of it will. The chloride part, once again, will not go through any type of hydrolysis. So we do have this guy that will go through hydrolysis and act as an acid. We also have this guy, which is a strong acid. So much like the previous titration, at this point, we actually will not really be too concerned with the salt, as again, it's got to go out and do a load of reaction. It's not going to generate anywhere near the amount of H plus in that solution as you dropping the HCl in there, right? So every time you drop the HCl, because it's a strong acid, it's going to completely break apart. So past the equivalence point, we will ignore the contribution of the salt. We will look really at just the strong acid that we have left over. And because it's a strong acid, that means we have some H plus concentration. And that means we could go directly into the pH, which we would expect again at this point, definitely to be acidic, as you're just dumping acid basically in there past the equivalence point. Any questions? Yeah. We discount NH4 plus because it is contributing, to the solution in terms of H plus, but it's not contributing anywhere near what HCl would be doing. So for example, if we look at what's happening, say with NH4 plus, is it's got to go find some water, it's got to do its reaction to generate that H3O plus. When we look at what you're doing really at this point is you're dropping the HCl, and all it needs to do is just go for a swim, and it will break apart into H plus. So because this is a strong acid, a strong electrolyte, as soon as you drop it in there, you just beefed up the H plus concentration. And it's really between the two, even though this guy is generating some, this is going to be where the major amount of H plus is coming into the solution, because it's a strong electrolyte and just going to break apart pretty much completely. Other questions? So as we can see here with this titration curve, it's pretty much very similar to the previous one we did, just sort of opposite. Like I said, the weak acid, strong base, we're going from acidic to basic. Here, we're going from basic down to acidic. So once again, to summarize the 4 spots at the very beginning, it's a KB type problem, right? You just got to do an ice table. Second part, you should hit a buffer no matter what happens, and it should be mostly a basic buffer. May jump into some acidicness near the equivalence point. At the equivalence point, you have a hydrolysis problem where you got a salt happening. And past the equivalence point, you really have kind of a strong acid sort of situation. So each of those steps requires an ice table. First one requires 1 ice table. Second one requires a minimum of 1 ice table in Henderson-Hasselbalch, or 2 ice tables, no Henderson-Hasselbalch. The third one requires 2 ice tables. First one to get the salts concentration. Second one, a hydrolysis ice table. Third one requires 1 ice table to figure out how much strong acid you dumped in there, basically, so that you could get to the pH. Any questions on any part of those guys? Yeah. All right, so let's see here. We have this example which you completed at home. Yes, I like it. All right. So did I, apparently. All right. So let's take a look at this one here and figure out what is going on here clearly. Now that I got rid of all my scribble, I can re-scribble on it. All right. So we're going to do this titration here of 0.1 molar nitrous acid. And we're going to titrate it with 0.1 molar sodium hydroxide. We're looking at the pH at a number of different points. So again, orientation purposes here, we have our sodium hydroxide up in the burette. Here we are adding it to our nitrous acid. We have a Ka value for our nitrous acid. So this tells us right off the bat, we are doing a titration of a weak acid because there's a Ka value, and sodium hydroxide is a strong base. So that's, again, a good thing to sort of think about. Once again, we should kind of know what's going on at each point in the titration, depending on where we're at, based on this type of titration. So we're going to start with the initial solution, which is A, and that is before the titration begins. So basically here, looking at A, we have 100 milliliters, I think, of 0.1 molar HNO2. They gave us our Ka value here, 4.5 to the 4. So obviously here, before we begin, which is pretty much what is happening here, we have just a weak acid, which means to find the pH at this point, before we add any sodium hydroxide, it's just going to be a Ka problem. So we would take our weak acid, we would break it apart into H plus and NO2 minus. And because we have not added any sodium hydroxide at this point, we're good to go with the molarity. So we could go right in with the molarity here of 0.1, 0, and 0. The change here, this is going to be x's, so plus x and plus x. This is going to be 0.1 minus x, x, and x. Any questions so far? This is going to go into our Ka expression, which is our H plus, our NO2 minus, divided by our HNO2, and that's going to equal our 4.5 times 10 to the minus 4. Popping in our numbers here, going to give us x squared divided by 0.1 minus x. I'm going to assume x is equal to 0 here, which would get me x squared divided by 0.1 equals 4.5 times 10 to the minus 4. Let's see here. Maybe there we go. 4.5 to the minus 4 times 0.1. Little square root action on it. Going to get us 0.00671. I'm going to divide that by 0.1, times it by 100, and now I'm going to be really upset in a second here. Probably. That is a bad assumption there at 6.7%. That's why we don't do problems in the morning. It's too early for this. All right. Well, we could just ignore it. No, I'm just kidding. All right. So we're going to go back because it's bad. Halloween bad. Here we go. We're going to multiply this to the other side and do our favorite thing, which is quadratic-y. And we're going to do 4.5 to the minus 4 times 0.1. And 4.5 times 10 to the minus 5, I think there. Equals, no, minus 4.5 times 10 to the minus 4. X equals x squared in this case. We're going to bring everybody to one side, so I'm just going to bring everybody on the left to the right, and that will give me x squared plus 4.5 times 10 to the minus 4x minus 4.5 times 10 to the minus 5 is equal to 0. This is going to go into our quadratic, which is minus b, right? Plus or minus square root of b squared minus 4ac divided by 2a. So that's going to get us a minus 4.5 times 10 to the minus 4 plus or minus, if we do the inside of the square root, give it a try, see what I get here. So we're going to square B. We're going to minus it from 4 times A, which is 1, and times it by negative 4.5 to the minus 5. Gets us a 0.0001802. We're going to square root it. Gonna get us, after we square root it, 0.0134. We'll call it, all divided by 2. Let's see how we did. Minus 4.5 to the minus 4 plus 0.0134 divided by 2 gives us an x value of 0.00648. And if we do, obviously, the minus part of this, we are going to get a negative number, which is no good, I'm assuming. So negative 0.00693. Clearly, we cannot have a negative number as we are looking for x in this case. So that means that that x value right there should be our H plus concentration, which means our pH would equal minus the log of 0.00648, getting us minus the log 0.00648, about a 219. Seems like a winning number. Any questions on that one there? Yeah. Did I make say again? In the quadratic, I did this part. I did. I did on my calculator, but I don't think I wrote it here, so that should be positive. There we go. I think I got the right number there, but I think I wrote negative, but should be that, right? Or not, maybe not. Maybe I didn't. All right. Thank you. Let's try that again. Good thing they invent racers. There we go. Let's try this again. Yes. All right. So I think I was right, actually, right? I was right, yeah. Because it was a positive number. So hey, I'm gonna erase my eraser. Let's try that again. All right. So it should be negative here, right? Because it is positive here, right? It's our B, right? So that means we should have negative 4.5 to the minus 4 plus 0.0134 divided by 2. So that was our correct x value, right? 0.006475. Again, the other one gives us a negative number when we do it, which would be no good. So our pH would be minus the log 0.006475. And that's going to get us there 2.19. All right. Back to 2.19. Yeah, it should be negative because this is positive here, right? In this case, yeah. Other questions? Okay. So that is part A. Again, really just a weak acid problem because we have not added anything to it. Let's take a look at B when we start adding. So in this case, we are going to add 80 milliliters of our base to our acid in this case. So clearly we have started the titration. So let's take a look at what happens at that part. All right, so B here is we added 80 milliliters of our 0.1 molar sodium hydroxide to 100 milliliters of 0.1 molar nitrous acid. Again, same Ka value, 4.5 times 10 to the minus 4, I believe. All right, so clearly we're going to get a reaction here, and that is not HCl. Oh, wow. All right, well, clearly I didn't sleep last night. Now let's try it again. You know, we all have those days, don't we? All right, so I'm gonna go with HNO2. Just gonna play the pre-recorded video in a second. It'll be all right. All right, so a little nitrous acid plus some sodium hydroxide. I'm thinking in this case we're gonna get some water going on and a little NaNO2 action happening. There we go. So clearly we're adding at this point, so we do need to do it in moles. So we need the moles of each of these. So I'll just do the hydroxide here, which would be 0.08 liters. We do have to convert it to liters and use the molarity of 0.1 moles per liter for our sodium hydroxide. That's going to get us 0.008 moles of sodium hydroxide. And obviously we'll do the same thing there for our nitrous acid. So we'll take 0.1 times 0.1, going to give us 0.01 moles. And we have 0.008 moles. So this is what we started with. This is what we're adding. I am before, or after, or at the equivalence point. And before, once again, if you're not sure you are, that number is less than that number, which means what we're adding is less moles than what we started with. So we're definitely at the before the equivalence point. That also tells us that the change should be the hydroxide in this case. So that is going to be our change. That means when we reach equilibrium here, go into the calculator here for sure. All right, we got 0.002 moles. We got nothing of that, 0.008 moles of this guy. At this point, like we talked about previously, we do want to convert back into molarity. It's just really good practice. So at this point, we started with obviously 100 milliliters of our acid. We added 80 milliliters of our base, which means we're at 180 milliliters total volume at this point. That needs to be converted to liters. So we'll divide by liters in this case. That's going to get us 0.002 divided by 0.18. It gives us 0.01111111. 0.008 divided by 0.18. It gives us the classic 0.0444 molar at this point. At this point, if you're not sure what's going on, which you should kind of be sure what's going on at this point, let's take a look and see what we got going. So we got this guy right here, and we got this guy right here. Those two guys are what? Are they a buffer? They are a buffer, and that's exactly what we should expect to happen at this point because we are before the equivalence point. The buffer part is not the sodium part, right? It's just hanging out. It's really the NO2 minus part, right? So the NO2 minus and the nitrous acid is a difference of 1H plus. The sodium's there just to balance out the charge. So that is our good friend, Mr. Buffer. So because it is a buffer, we can go into the Henderson-Hasselbalch equation. Once again, you could do a Ka table with HNO2. You want to make sure you have initial on both sides if you choose to do that. But I'm going to do the Henderson-Hasselbalch, which is our pKa plus the log of the base over the acid. We do need a pKa value here. So pKa would be minus the log of 4.5 times 10 to the minus 4. And that's going to give me 335 looks like. So putting that in will get us 335 plus the log. Once again, the base here is our sodium nitrite, as that's nitrous acid. So that would be the acid. The guy with the spectator ion is usually the base in a lot of cases. So we do want to make sure we put that guy up on top, which would be 0.0444. divided by 0.0111. And let's see how we do here. 0.0444 divided by 0.0111. A little log and a 335. It's going to get us a 3.95 at this point in the titration. So pH is going up, which is what we would expect since we're adding base. Not a tremendous jump because we're in a kind of the buffer region at this point, right? So again, it's going to kind of maintain until you sort of blow through the buffer part of it. And then it's going to have that jump to the equivalence point, which is as we're going up the curve. So if we're going up the curve, again, here, we're kind of in this area here where it's slowly rising because of that buffer. We're very shortly going to be shooting into the equivalence point where we're going to see that jump in pH that's going to happen. Any questions on that one there? So let us do that, which is the equivalence point, which is the next one. So we are at that point where we're going to shoot up in pH as we approach the equivalence point. So here we're adding at the equivalence point, we're looking for the pH, and we have 100 milliliters of our 0.1 molar nitrous acid with our 0.1 molar sodium hydroxide. How much volume do I need to reach the equivalence point in this case? You will need 100 milliliters. And that is because they are actually the same concentration, and it is a one-to-one relationship, which means you need equal amounts to get there. Once again, if you weren't sure of that, let's take a look at another way we can figure that out. Again, we will need to do our reaction here. We will do our moles. So we do need the moles of our acid, which we could clearly get, which is the same that we started with before. Now, at this point, if you weren't sure that you need 100 milliliters, the thing that you should know of is you're at the equivalence point. So the moles of the sodium hydroxide you need should be the exact same number. So even if you weren't sure of our 100 mils, you do know that you do need 100.1 moles of our sodium hydroxide. Now, if we look at our sodium hydroxide, we know that we need 0.1 moles of it. We do have the molarity, which is 0.1 moles per liter, and that's essentially going to give us 0.1 liters, which is 100 milliliters. So alternative to that, you can use the molarity, which is the molarity of the sodium hydroxide, and the moles that you need to figure out the volume. So again, those are two ways that you could do that. Also, one-to-one relationship, you could use this as well to figure out how much to get there. So any of those three ways should allow you to figure out you need 100 milliliters to actually get there. Any questions on any of those ways? All right. So we have 0 that. We can't choose the wrong number since they're both the same numbers. So that's going to be our change. That means at equilibrium here, we have nothing of this guy, nothing of this guy, 0.01 of this guy. We do need to convert back to molarity. So we're looking for total volume. So we started with 100. We added 100 that we figured out, which means we should be dividing here by 0.2 liters to convert it back to molarity. So 0.01 divided by 0.2 going to give us 0.05 molar. At this point, the only thing left is our salt. Will the salt do anything? That is both answers, I think, but this salt will do something because it is basically a sodium ion and a nitrate ion, right? Or nitrite ion. That guy will not because it's group 1, but this guy, as we know, comes from this weak acid, which means it will go through hydrolysis. So this is the part of the titration. Also knowing that we're at the equivalence point, we should have a hydrolysis problem happening, which is what we do have here. So again, as I talked about, knowing where you are in the titration, knowing what type of problem it is, makes the calculation part easier because you should know what you're doing. So in this case, we would expect our nitrite here to react with water. Clearly, the nitrite has no hydrogen, so that makes it also pretty straightforward. It cannot donate something it doesn't have, so it's got to accept it in this case. And it will make our HNO2 and a little hydroxide. Not to mention that it comes from a weak acid, which means this is going to act as a base, and a base will accept the H plus coming back over. We're going to take our initial concentration that we got up here, which is why it's important in this case to convert it back to molarity. You do not want to be running through the second table here in moles. So you want to make sure that you have converted it back to molarity at this point. And because we're back to molarity, we could do the rest of this with X's. So minus x plus x plus x. Going to go 0.05 minus x, x, and x. Any questions on that table there? That is going to go into our K expression of our products over our reactants. K, A, B, C, D, E. KB, we know that this thing should be basic, and we know we should be using a KB because of the hydroxides being produced. That means we also have to flip this guy, and that means that our KB in this case would be our KW divided by our KA, 5.4 times 10 to the minus 4. Hope, yeah. So that's going to get us 1 to the minus 14. Divided by 5.4 to the minus 4. We're going to go with 1.9 times 10 to the minus 11. So really important thing people always sort of forget at this point is they just roll with that Ka value that they were given, which obviously would not be good. And I did it backwards. I knew I did. That's all right. Thanks for not telling me. That's all right. Want to wait until I got further down in the calculations. See, even I don't know what I'm doing. All right, 4.5 times 10 to the minus 4. Let's try that with the right number there. I recommend pencils for the rest of your note taking for the rest of the day here. Let's see here. Let's go with 2.2 times 10 to the minus 11. All right. So putting this in can give us x squared. 0.05 minus x is equal to 2.2 times 10 to the minus 11. All right, I'm going to assume and hope for a better outcome here. So let's go. Let's assume that x is equal to 0. That's going to give us x squared divided by 0.05 equals 2.2 times 10 to the minus 11. So we're going to multiply the 0.05 to the other side. I'm also going to take the square root of it. And if you do all that, we will get an x is equal to 1.05 times 10 to the minus 6, I hope. We're going to divide that by 0.05 and times it by 100. And thank goodness the check is good. In this case, it's not even 1%. So we are good. That means that that is not our H plus concentration, right? But that is our hydroxide concentration in this case. So that means that our POH will equal minus the log of 1.05 times 10 to the minus 6. And that's going to get us a 598, I guess we'll go with. Once again, if for some reason you thought that was the pH, it should not make sense to you, right? Because it should be basic at this point, right? So we're going to subtract 14 from that. And if we do that, our pH will be 14 minus 598. Going to clock us in at a pH of 8.02, which is basic and what we would expect. So we just went from 80 milliliters where we're hanging out at a pH of 3 and some change, right, in that buffer region, to now hitting the equivalence point where clearly we're going from kind of rising and now jumping, right, to the equivalence point. And that's what we see at the equivalence point is basically what just happened is we just blew through the buffer, right? And at this point, we blew through the buffer part of it, and you're really now back to just adding more HCl, so more sodium hydroxide, so that pH is going to basically jump pretty high in this case. Any questions on any part of that there? All right, here. I can go for part D here and try to do it all once. Here we go. Let's do part D, which clearly I imagine we are past the equivalence point at this point. And what are we adding there? 105. That's the winner. All right, so we are adding 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar HNO2, 4.5 times 10 to minus 4 Ka. All right, so once again, same reaction happening. We are going to obviously do it in moles here. So our moles 0.1 times 0.1, which is the same one we've been starting with, 0.01 moles. Our sodium hydroxide 0.105 times 0.1, 0.0105 and 0. So again, if you were still not sure where you were in the titration, obviously we are starting with this guy, we are adding this guy. And if we compare the moles of each of this, we actually have more moles of sodium hydroxide than we do of the nitrous acid, which means we are definitely past the equivalence point in this case, as we have more moles. That's the point where our substance that we're adding becomes the excess reagent, and the guy that we started with is the limiting reagent. So the change here is going to be the acid in this case. That's going to get us none of the acid, which all gets used up. We will end up with something 0.0005 moles and 0.0100 moles. This guy. Total volume at this point is we started with 100. We added 105 milliliters there. That is a 205 situation, I think, for our total volume. We're going to divide these guys by 0.205 liters. We do need to convert it to liters to do that. So that will get us 0.00244. And for the other guy there, will get us 0.0488. At this point, if you're not sure what's going on, we got two things left over. First off, is that a buffer? It is not. So remember, just because you have two numbers, don't use them. Yeah. In the Henderson-Hasselbalch equation. So it's not a buffer. We do have two bases happening here. We have, once again, our salt that will act as a base, and we have this guy, which is a strong base. So as we talked about, since we're past the equivalence point, we're not going to worry about the contribution from the salt, as it will be much less than the sodium hydroxide, because once again, much like the HCl we just talked about, sodium hydroxide just needs to go for a swim. It's going to produce hydroxide and all that. So that means that this is going to equal our hydroxide concentration, and we can go into our POH at this point. Minus the log here, 0.00244. That's going to give us a POH of 2.61. Once again, we're going to subtract 14 from it there. That's 1139. Seems very basic, which does make sense since we're past the equivalence point and basically just dropping base in there, right? Any questions on that there? All right. Questions on titrations. You need to know, obviously, those three types of titrations we talked about. You do need to know what the curves look like, and obviously you need to be able to calculate the pH anywhere along the curve. Any questions on how to do any of that there? All right. So dare I say, to finish up chapter 14 here, we're going to talk about a little bit here. We sort of talked about as we've been going through, but acid and base indicators. As we talked about, acid and base indicators, they work really over specific pH ranges, and they typically will change colors within a specific pH range. And they're really like weak acids. So that's what this sort of shows. There's a protonated form of the indicator. IN is the indicator here, and it has an H plus on it. And there's a deprotonated form of the indicator where the H plus comes off. So there's kind of an acid form of the indicator and a base form of the indicator. And if the concentration of the acid form to the base form is greater than 10, then we'll kind of see the color in the acidic solution, and vice versa. If it's less than 10, we'll see the base predominate. So here's a list of ones. You can see some change multiple colors, some change kind of one color. Like, for example, crystal violet, it's kind of, there's some yellowish to greenish to bluish, depending on where you're going. But it works in a very acidic range, which obviously is in this range of like less than 2 in terms of the pH. We have something like thymol blue here, which goes from like red to kind of an orangey color, also acidic. There's our friend phenolphthalein, right, which, as you can see, is really colorless through most of the eighths and then gets very faintly pink towards the mid eighths and above, and obviously gets very pink if you go above that. So when we choose an indicator, as we talked about, what you want to choose is one where you would see a color change near the equivalence point. And you could dial it in. As you can see, there's a lot of different indicators you use. Sometimes people think it's only phenolphthalein, but there is obviously a truckload of indicators that you could use that will change color. And you could actually do a theoretical calculation of your titration and have an idea as to where you would expect the pH to be at the equivalence point. And you could really dial into a pretty good indicator. You could also just generically think about what should happen at the equivalence point. So if you think about the three types of titrations we talked about, we have an equivalence point where it is neutral, right? And we have an equivalence point that's acidic, and we have one that's basic. So thinking about what type of titration you're dealing with and what you would expect in terms of it being acidic, basic, or neutral can also help you just broadly choose an indicator that probably would work in each case. And like I said, you can get very specific by taking a calculation and really going, okay, this one changes exactly sort of in that range where I would expect it to be. Maybe this one's actually a little bit better to use than another. So for example, here, if we have this list of indicators, as you can see, we have the color in acidic solution and basic solution. If we were doing this titration, what indicators would be an okay choice in this case? Just did, right? So this is, we got our KOH instead of sodium hydroxide, but we're adding it to our acid. That is what type of acid? It's a weak acid, and that is a strong base, right? So we should know that when we reach the equivalence point, should it be acidic, basic, or neutral? Should be basic, because as we just saw, when we hit the equivalence point, we will have a salt that will go through hydrolysis and it will generate hydroxide, which means it should be basic. So if we look at this list here, thymol blue works really great in an acidic range, probably not going to be a good choice. That will have changed color well before you get near your equivalence point. Same thing with this one, will also have probably changed color before you get there. That one as well, that one, and this one would all probably have changed colors before you needed to do so. So since it is basic, probably these two would be the good choice. And again, the creosol red is 7.2 to 8.8. So depending on sort of how basic you are, it might actually change color too soon for you, right? So this is where you can really dial it in and do that calculation and go, oh, well, my equivalence point should maybe be more closer to 9. So maybe phenolphthalein would work better than creosol red, which even though it does turn basically, our basic solution, it may turn too soon for you. So broadly speaking, since we don't know the parameters of obviously the titration we're doing in terms of concentration or volume, we would want to choose something that's basic. And like I said, if you did the calculation like the one we just did, we had, what was it, 8 point something at the equivalence point, 8.02. So for example, even the one that we just did, you know, at 8.02, again, that creosol red might be a little too far gone at that point for you to visually see it, right? So we do want to look for something where we can visually see that change near the equivalence point. Any questions on how to choose indicators? All right, dare I say it, that is chapter 14. Who would have thought it ever end? All right, so chapter 15, which is actually quite short. It's a good deal. So we went from extremely long to perhaps sort of short. We're going to talk about two other sort of equilibriums to add to our ever-growing list of Ks. We have Ka, Kb, Kc, Kp, Kw. Let's add Ksp and Kf to it because we want to use the rest of the letters in the alphabet here. So we're going to talk about really two types of equilibrium. This Ksp is about solubility, and Kf is actually about complex ions. So these are two equilibrium constants for the formation of complex ions and also solubility. We're going to start with solubility, which is what Ksp stands for. Ksp stands for solubility product. And when we have something that is, even as you remember from your solubility rules. Yes. Did you have to learn the solubility rules? Did they just give them to you? You had to memorize it? Wow. Impressive. They didn't. No. There's a lot of no's. I mean, clearly you chose wrong for Chem 50. No, I'm just kidding. But you should know these things, hopefully. If not, you might want to refresh, but there's a lot of ways that you could probably figure it out based on what we're doing. But KSP is solubility products, so things like your solubility rules of things with nitrate, group 1, ammonium, acetate, those things are soluble in everything. Things like chlorides, bromides, iodines are soluble in everything except for like lead, mercury, and silver. Even things that technically based on solubility rules are said to be insoluble will have some degree of solubility. So everything, even though we call it insoluble, there's going to be a little bit of it that will break apart in solution, super small amount in a lot of cases. And that brings us an equilibrium. Like we look at silver chloride, which based on solubility rules is a insoluble solid, but in solution, a tiny bit of it will break apart into silver ions and chloride ions, and we'll set up an equilibrium. And that equilibrium is just like we normally would do. We would write our products over reactants, except in this case, our reactants are solids. And that means that typically when you write a KSP expression, it's pretty much all just products. So typically when you write the reactions, you have solids on the left and aqueous ions on the right. And that means that usually your KSP expression will only be the products. You still do everything like normal, which means if you have coefficients, you should include them. So when we have something like magnesium fluoride, you get 2 fluorides for every 1 magnesium. You do need to include it into your KSP expression because it is still an equilibrium expression. This guy's got 2 or 1 coefficient, so you would include it there. This one has 2, which would also be included. So they are equilibrium constants, but because they are KSPs, they're sort of the equilibrium constant for things that are insoluble. So things that we normally think about as being solids and insoluble, we could have this equilibrium that happens for it. Because these things are typically insoluble, if you had to take a guess, would the KSP values be large or small? Be really small. So usually KSP values are extremely small, like to the -32 or something like that. So really small values. And that's what we typically will see because they are mainly hanging out over here on the reactant side, which means we have more reactants than products, and it's usually will be much small. So we can use our KSP and our good friend Q, which we also saw in a previous sort of chapter, to decide whether or not you would expect a solid to form. So if you calculate Q, which is done the exact same way as you calculate KSPs in this case. So Q is this calculated the same as your products over your reactants, and in most cases, your reactants will be solid, so it'll be just products. You calculate the exact same way as the KSP. And if you calculate Q and it's less than the KSP, you have an unsaturated solution, right? An unsaturated solution means you could continue to get things to dissolve, right? And things will continue to dissolve until you hit a saturated solution, right? So an unsaturated solution, you'd expect no precipitate to form. So if you calculated Q and it's less than the KSP value, you would not expect that solid to form. If you calculate Q and it does equal the KSP value, then you're pretty much at a saturated solution. You're pretty much right at that point where if you add any more, you should expect solid to form, but you haven't got there exactly yet. So you pretty much have dissolved the maximum amount of solute that you can at a given temperature. And if you calculate Q and it's greater than the KSP, you have a super saturated solution, which is like a saturated solution, but just super. That is a solution. That is a solution. It sounded so much better in my head. That is a solution that you have way too much solute dissolved in it, right? It's an unstable solution, and you pretty much would expect everybody to precipitate out. Perhaps you remember a supersaturated solution of sodium acetate, where you have it and it looks like a solution. You have like one little crystal to it, and all the solid comes out. Yes, they do that experiment or show that. Yeah. So what are some factors that affect whether or not you will see the solid or not? So sometimes people think based on solubility rules, they are 100% always correct. It's always going to happen. So sometimes people think if I take silver and I take chloride under any conditions, I put them together, I will get a solid that forms. And that's not always the case. So there's a lot of factors that actually affect solubility. And we're going to talk about several of them as we go through this chapter. But things like the concentration of the ions that are floating around are really important. Things like pH, for example, is important. Things like common ions are also play a role in terms of whether or not perhaps you would see a solid form or not see a solid form. So there are certain things that are technically insoluble based on solubility rules, but because of the conditions actually can be quite soluble when they come together, or you won't see that solid form. So those are some of the things that we'll be looking at as we go through this. Here's a table which you clearly could see all the numbers. You probably can, you're young. But if you look at some of these numbers, or if you look in your book, a lot of them are, again, very, very small numbers for our KSPs. And that is because it's mainly staying together because these are things that are typically insoluble. That does have an effect on some of the calculations that we do. So let's talk about some common calculations that we do. And that is one of two sort of solubilities we calculate. We calculate sometimes the molar solubility, which is really the molarity, which is the moles of solute over the liters of solution. So the molarity. And sometimes we just look at the solubility in grams per liter, which is basically how many grams of that guy that you could get to dissolve in a liter of solution. So there's kind of two approaches that you take to these type of problems. One involves an ice table that you do need to do an ice table, and one you could do an ice table, but you don't necessarily have to do an ice table, but sometimes it helps to kind of do it. So one type of problem is they want you to basically calculate what is the KSP of that particular compound or that solution. And they typically will give you the solubility. So sometimes they may give you the solubility in grams per liter or some other unit, but you want to convert it into molar solubility, which is the molarity. You want the concentration of the ions, and then you want to go into the KSP expression. By the way, what is the thing that ties both of these solubilities together? If I need to go back and forth. What is it? How do I go from, say, grams per liter to moles per liter? I need the, yeah, we need the molar mass. So the molar mass is the thing from the periodic table that basically ties both of those things together. So that's also how you, obviously, in a lot of cases, you may go from here to there, is to use the molar mass to figure out the molarity of everybody. The second thing is the only thing that's given to you is just the KSP value. So that's like the only thing given to you. And they want you to figure out what the solubility of the compound is. In that case, that's definitely an ice table situation. So this is definitely an ice table situation. This is an optional ice table situation, but can be helpful to maybe see you visualize things. It is very common when we do these type of calculations. There's places where perhaps you need to multiply something by 3 and also cube it. And sometimes what happens when people do these problems is they go, well, I multiplied it by 3, I don't need to still cube it, or I cubed it, I don't need to multiply by 3. So sometimes even doing the ice table for sort of the first approaches we'll see can sort of help you not miss sort of some of the calculations that you need to do. So let's take a look at one here together with the dramatic pause there of silver phosphate. At 25 degrees is 1.6 times 10 to the minus 5. We are looking for the KSP in this case. So we're given the solubility of this, and I'm going to show you the ice table way, and then I'll kind of show you how you might not have to do the ice table in this case. So in this case, we're given the solubility. So the first thing we want to do is write the sort of equation of what's going on. Since we are looking for a KSP, by the way, even if you don't know your solubility rules, you can make a pretty good assumption that that's probably going to be insoluble. So this is a good way to think it. When this breaks apart, we will get 3 silver ions and a phosphate ion. We could write our KSP expression for this, and that would be the silver concentration cubed times the phosphate concentration. Once again, here our solid there's on our reactant side, which means we're not going to include it, obviously, like normal, since it is still an equilibrium constant. So a reminder that any K value, be it Ka, B, C, P, SP, F, whatever it may be, they're all just the same thing. They're all just equilibrium of products over reactants. So they're all basically the same thing. So in this case, we're going to actually do an ice table. I'm going to show you the ice table and how it's slightly different than how we do some ice tables in other situations. The difference is we kind of use a different letter a lot of times, so I know it's surprising. So we're going to start like normal, which means these guys are going to be 0. I'm not going to worry about the guy on the left because it is a solid, right? So might as well not worry about him. Now we have this reaction, and normally we go minuses on the left, which I'm not going to worry about, but we will get some pluses on the right. We could think of this as this guy just went for a swim, so some of it's going to break apart, right? So that's the pluses. So instead of using X, what we typically use here a lot of times is the letter S, because it mixes things up. S stands for molar solubility. I know it's change, it's okay. And that is basically the molarity of what we're looking at. We do it the same way as we do X, which means we still need to take into account the coefficients when we do it. So this would be plus 3s, and this would be plus s. That means when we come to equilibrium, this would be 3s and s. Any questions on the ice table? Now, normally at this point, if we were given the KSP, we would go into our KSP expression, which in this case would be the KSP would equal our 3s, and we do need to cube it, times our s, and that would equal obviously our KSP, which is actually what we're looking to find in this case. So this is what the ice table would look like if you were given the KSP and nothing else. You should do this. You would then have the KSP, and then you could solve for S. And when you solve for S, that would give you the molar solubility of that compound. Now, since we're looking for the KSP, we're looking for the molar solubility, we are actually given the molar solubility right here, right? That is basically S. That is the molar solubility and molarity. So at this point, what we could do is take 3 times 1.6 times 10 to the minus 5 molar, and times it by our 1.6 times 10 to the minus 5 molar. We really don't need the units because it is still an equilibrium constant, which means there's going to be no units as well. I'm going to cube that. Dramatic pause. Thank you. Here we go. We're going to take 3 times 1.65. Wow, I can't do much today. All right, 1.6. That's what happens when you have candy for breakfast. I don't know. All right, so we can take that. We're going to cube it here. We're going to times it by 1.6 to the minus 5. And that's going to give us a KSP in this case of 1.8 times 10 to the minus 18. First off, any questions on that? Yeah. Yeah. It does. So it's the exact same way that we do with the X. So just like what we do with the X's, we take the coefficients, whatever they are, is where that comes from. Yeah. It does. So that's a good question. And this is why I would probably recommend, even though technically speaking here, you don't really need to do an ice table. By doing the ice table, you can visually see I need to multiply it by 3, and I also need to cube it when you do that. And it's very common that sometimes people in this case, like I said earlier, will either cube it and not multiply by 3, or multiply by 3, forget to cube it, and stuff like that. So visually, if you do the ice table, it helps to kind of remind you, hey, I need to kind of multiply that number by 3. The alternative approach is if you understand sort of concentrations, which is kind of the same thing. We know that if this guy was, we have this. We know that this is 1.6 times 10 to the minus 5. As we talked about, it's a 1 to 3 relationship, right? So you can take that for the silver, and it's a 1 to 1 relationship, which means this guy would just be the same concentration. And then you could go technically directly into this, and it's basically the same thing as the ice table. if you understand the concentrations and how they work when they break apart into ions. Again, I would probably recommend just doing the ice table in this case because it helps catch hopefully some of those errors that people commonly make. But if you understand how it breaks apart, you could just go and figure out the concentration of the individual ions and go right into the expression and solve for the KSP, which is essentially what the ice table does. Just kind of puts it out there a little bit easier to see. Any questions on that one? Large value of KSP or small? Small, right? So again, this thing is pretty much insoluble, right? To the minus 18 means it's pretty much staying on the left-hand side. Only a super small amount, right, is breaking apart in solution. All right, why don't you try one more here? What is the solubility? Let's do grams per liter of grams per liter of silver chloride. Silver is 107.9. And chlorine is 3545. Okay, let's take a look. So silver chloride is what we want to start with. So we'll start with that formula, which should be this guy here. It is insoluble. Based on solubility rules, it will break apart into a silver ion and a chloride ion in this case. We have the KSP value given to us. The KSP expression would be our silver times our chloride, and it would equal this guy here. Once again, here, obviously, our reactants is solid, so we're not going to do anything with it. In this particular case, we're just given the KSP, which pretty much means you should do an ice table because you have no other values given to you. So this is going to be 0 and 0. The change here is going to be plus S and plus S. Once again, the coefficients here is 1 for each of them, so we just have 1. We're going to have S and S in this case. Any questions on that one so far? At this point, we're going to go into our KSP expression, which will give us S squared is equal to 1.6 times 10 to the minus 10. Again, basically putting these guys in. Pick the right arrows, whichever way you want to go with that. We're going to square root it there. Do a little square root action on both. Grab the calculator. Gonna go 1.6. No, gonna square root first, and then go 1.6 to the minus 10. Going to get us something like 1.26 times 10 to the minus 5. This would be molarity, right? Or 1.3 times 10 to the minus 5. And that would be molarity, as that is the molar solubility of it. And that would be the molar solubility of silver chloride. Now you may be asking, isn't that these guys here, which is the silver concentration and the chloride concentration? And the answer is yes, it is both of those guys' concentration in the solution. And if we go backwards, it is a 1-to-1 relationship between any of those guys there. And that would also give you the molar solubility of the whole thing. Typically speaking, when you solve for S, that is pretty much the molar solubility of the whole thing together. Yeah. And it's also can be the individual ions in this case as well. It's the molar solubility of the individual ions in this particular case. So because of that, that means that is really 1.3 times 10 to the minus 5 moles per liter of silver chloride. Once again, as we talked about, to go from moles to grams, we do need the molar mass. So that's a 107.9 plus 3545, going to give us 143. Let's just add that together. 143.4 grams per mole. So we'll use that as a conversion factor here. 143.4 grams per mole of silver chloride. The moles will cancel, and that will get us 1.3 to the minus 5. Approximately 0.00186 grams per liter. Any questions on that? Is that really soluble? That is not very soluble. That means you can manage to dissolve about 0.002 grams in 1,000 milliliters of water, which is not very much at all, right? So That's why we consider silver chloride to be insoluble, because that's very, very little solubility. Also, though, demonstrates the idea that even though it is insoluble, there's still a smidge of it, right, that you could technically, or is basically dissolving in that solution. Any questions?